In our last video for Chapter 19, we're going to be looking at learning objectives 5 and 6. From here, we're going to look at Gibbs free energy under non-standard conditions and relating Gibbs free energy change with our equilibrium constant. Okay, so with non-standard conditions, we're talking about if we're not at 0 degrees or not at 25 degrees Kelvin or 25 degrees Celsius, or if we're not at 1 atmosphere. So we're not at our regular conditions. We have an equation where we have delta G is equal to delta G naught plus RT ln Q. So this takes into account our temperature and if we're at different pressures using our Q, our reaction quotient. So using the reaction quotient to look at non-standard conditions. So if we have a Q that is much less than 1, then RT ln Q will be much less than 0. So delta G will be less than 0. So it should spontaneously proceed forward. However, if Q is much greater than 1, then RT ln Q will be much greater than 0, so delta G will be greater than 0. Not good, so we're going to be spontaneous in the reverse direction. Okay, so let's try this out, try using this equation. So we've got delta G naught at 298 Kelvin. We want to calculate that value, and we want to calculate our G, just a regular delta G, so our non-standard G, for the reaction 2 NO2 gas goes to N2O4 gas, and we'll have the following pressures: 0.4 atmospheres and 1.6 atmospheres for NO2 and N2O4 respectively. So if we looked at this, we're given pressures so we can solve for Q. So when we're looking at our delta G of our reaction, delta G naught of our reaction plus RT ln Q, we're given the information to solve for Q, we're given T, we have R. We want to solve for these two quantities. This one can be solved because we have our reaction. We can just use our table full of stuff to figure that out. So let's go ahead and start here. So our delta G naught of our reaction is just our products minus our reactants. So it's going to be our products. So we have 1 mole of N2O4. And it has a delta G of 97.89 kilojoules per mole. And then we'll subtract our 2 moles of our NO2 times by its delta G, 51.31 kilojoules per mole. It's a little hard to see. Let me just clean that up a little. There we go. And that gives us a delta G naught of our reaction equal to negative 4.73 kilojoules, or negative 4,730 joules. We can also solve for our Q. Our Q will be equal to our partial pressure of N2O4 divided by our partial pressure of NO2 squared. which will equal 1.60 divided by 0.40 squared, giving us a value of 10. So we put that in. Our G reaction is equal to negative 4730 joules per mole. To use this equation, this has to be in joules per mole. And just when we do this, assume that we're talking about reaction proceeding with the amount of moles in the chemical equation. So this is the only time where we have to convert from a joule into a joule per mole, because our equation requires us to be in joules per mole so that our units cancel out, because of our R value right here. 8.314 joules per mole times by Kelvin, and that's multiplied by our temperature, 298 Kelvin, and our ln of our K, which is 10. When we solve all this out, we get a delta G of our reaction equal to 975 joules per mole. So we have a non-spontaneous reaction now. Spontaneous prior, but we've gotten to a Q value that caused us to not have a spontaneous reaction. Okay, moving on. We can look at our free energy in terms of equilibrium. So when we have a equilibrium process, we have a reaction where we start out in the spontaneous direction until we reach our equilibrium point. If we go beyond that equilibrium point, we're spontaneous until we get back to that equilibrium. So basically, at equilibrium, our delta G is 0. Our non-standard delta G is equal to 0 when we are at our equilibrium point. However, our delta G naught can be related to our equilibrium using an equation. So we're going to take this equation, and this is equal to 0 at equilibrium. So our non-standard delta G is 0 at equilibrium, and this becomes K at equilibrium. So if we take our delta G, set that equal to 0, we can relate our standard delta G to our equilibrium constant by the following equation. So, as I said, we're going to use this. From here, we can look at our delta G, our standard delta G versus our equilibrium constant, and solve for one or the other. And we can look at the relationship right here. So if we have a delta G that is less than 0, our ln K has to be greater than 0, which means our K is greater than 1. And we have mainly products. If we have a delta G that is greater than 1, so it's positive, we have an ln K that is less than 1, which means we have a K that is less than 1, so we are mainly reactants, which should make sense, right? If we are mainly products, we're going to favor our forward direction. If we are mainly reactants, we are going to favor our reverse direction. So the reverse direction would be the favored process. And then if our delta G is equal to 0, our ln of K equals 0, and our K is equal to 0. So we have equal amounts of reactants and products. Okay, so if we want to find delta H and delta S from temperature and Kelvin, we could take the equation we just used and take and rearrange it. So let's rearrange that equation. So I've just kind of switched the positions of things. And when I do that, I get ln k. So this we're going to replace with delta H naught minus T delta S naught. And we get negative delta H naught minus T delta S naught, all divided by RT. And then we're going to take this ln k equals negative delta H naught over RT minus T delta, plus T delta S naught over RT. Cancel out those T's, and we get ln k is equal to negative delta H naught over RT plus delta S naught over R. So we can actually plot this and get our enthalpy and entropy if we take ln k versus 1 over T. Just in case you want to know. Okay, so let's try one more example in this chapter. We're going to calculate the equilibrium constant K and delta G naught at 298 Kelvin for the reaction 3C2H2 goes to C6H6. So if we want to solve for this, let's first look at our equation that relates delta G and our equilibrium constant. We want to solve for delta G naught of our reaction and K. We have R and T. This can be solved using our regular means, where we take our products minus our reactants So let's go ahead and do that. So our delta G naught of our reaction is equal to 1 mole of benzene times by 129.7 kilojoules per mole. Our formation, Gibbs free formation, minus 3 moles times by 209.2 kilojoules per mole to get our ethylene. And this, when we solve it out, we get a delta G of reaction equal to negative 497.9 kilojoules, or negative 497,900 joules. And again, since we have R in here, we're going to have to convert that joules into joules per mole. So when we put this in to this equation, we're going to put it in as joules per mole, assuming it means per moles as written of the equation. 497,900 joules per mole is equal to negative 8.314 joules per mole times by Kelvin. And then our temperature 298 Kelvin, and then ln K. And when we solve for this, we get a K value equal to 1.89 times 10 to the 87, which means that this is really a one-way reaction. Okay, just some closing thoughts before we go and end chapter 19. Kind of just summarizing everything we've kind of looked at. So if we have a spontaneous process, it occurs without any helps. It occurs without outside assistance. And we could look at our standard molar entropy. Alright, so that's 1 atmosphere, 1 atm, and 25 degrees Celsius. And everything has a standard molar entropy. So everything has entropy except for a perfect crystal, right? So despite, or except for the one substance, everything else has entropy. But it's going to be highest for gases, lowest for solids. It increases as temperature or volume increases for our system. And then anything, a compound will have a higher entropy, entropy than a elemental form usually. So NO is higher than N2 or O2, and then more complex usually is higher. So CO2 is higher than CO. Generally, larger molecules or atoms will also have higher molar entropies. So, just as a, kind of when you're looking at something to try and decide if something has more disorder, you can look at that. And then, end of our review, let's look at our equations. So, if we have a delta S of universe, we have a greater than 0 if it's spontaneous. Our delta S of our universe is equal to our delta S of our system plus our delta S of our surroundings. Our delta S of our surroundings is equal to our negative delta H of our reaction over temperature. Our delta S of our system is equal to the delta S, sorry, not delta S, excuse me. Our S naught of our products minus our S naught of our reactants. We also looked at delta S of our system being equal to our delta H divided by T for a phase change. And then our delta S of our system is equal to N R ln V2 over V1 for the expansion of gas. Some other reactions that we looked at. We looked at our delta G of a reaction, and it'll be less than 0 if it's spontaneous. And we looked at delta G equals delta H minus T delta S. We can of course have the standard form of this equation. Right? And we have delta G naught is equal to delta G naught of our formation of our products minus delta G formation of our reactants. And looking at standard versus non-standard conditions, or if we have standard conditions, looking at our equilibrium constant. Those are our equations for Chapter 19. And that's everything. See you guys later.